Now you'll notice in the previous problem here I didn't worry about the rails on the op amp, and in general here with these filters we're not going to worry about the rails so much. We're going to assume that the power supplies are whatever they need to be. We're really just focusing on the design of the filter, the cutoff frequencies, and the gain. So let's look at another example here. Let's design an active low pass filter with the magnitude of the gain in decibels being 30 decibels and the cutoff frequency being, oh, let's just pick 14 kilohertz. So with this design here, we know what the circuit's going to look like. The circuit's going to look like this. We know this is what my ultimate circuit's going to look like. Now there's three key things we have to account for here. Well, not three, there's three key parameters. There's three things we have to find. But we want to remember here that my gain is negative R2 over R1, and that my cutoff frequency is 1 over R1C, which you could also write then in hertz as 1 over 2 pi R1C. Now technically we could design for any one of these to start with, but I always like to, when I'm looking at equations like this, I want to think about, okay, well, these are just resistor values. So as long as I make R1 reasonable, I'm automatically going to get R2 reasonable. Or if I make R2 reasonable, I'm automatically going to get R1 reasonable. It's not going to be too difficult with that. But so what I really want to do here is I want to start with this equation because we want to make sure that the capacitor and resistor values are quote reasonable in the sense that, yeah, you could use large values of capacitors. I mean, you can get, in the lab we even have like 470 microfarad capacitors, which is fine, except those are large capacitors, electrolytic, and why use that if you could get away with something like, maybe a 100 nanofarad or 1 microfarad or something of that nature, because using a smaller value, especially if you're using like a 100 nanofarad, 0.1 microfarad, those, if you're talking about building a board, they're smaller components, and not only that, but like they have chip capacitors and chip resistors, so they can be really small when you're designing a board and layout, because it's not just about picking components when you're trying to do final designs. Components are great, but you also have to think about, well, how much space am I going to be allowed on this board? Which also is sometimes when you want to worry about component count as well, because if you have a large number of components, and you don't have very much space on your board, you're going to run into some problems. Alright, so let's get to the design here. So again, it's pretty straightforward. What I'm going to do here, which is what we've done several times before, is that I'm going to actually compute R1C. And what I'm going to do is, well, R1C is going to simply be equal to 1 over 2 pi times F. And the reason I do that is then when I compute R1 times C, when I see that number, it makes it, for me at least, much easier to see what reasonable values would be for this. So let's go ahead and do that. So this would be 1 over 2 pi, and what was the frequency I chose? 14 kilohertz. And let's see what this value would be here. Let's go to our calculator. 1 divided by 14,000 divided by 2 divided by pi. And we get 1.137. 1.137. 1.137 times 10 to the negative fifth. And this would be, technically this is in seconds per radian. Now I'm going to convert that to engineering notation. I prefer things in engineering notation. It's just the Windows calculator doesn't do that automatically for me. So if I want this to the sixth here, I'll divide by 10. So this would be, wouldn't this be point? Wait a minute, let me think about this for a second. Yeah, space there for a second. This would, I don't know why I couldn't figure this conversion out. Maybe it's because it's early in the morning when I'm making this video. So this would convert to 11.37 microseconds per radian. Okay, but now if I have R1 times C here, this becomes kind of, easy to see what maybe some reasonable values were here, because if we think about this just off to the side here, if R1 is in the kilo ohm range, like single kilo ohm, well, you would have microsecond divided by kilo ohm, which was going to give you nanofarad, because you have 10 to the minus 6 divided by 10 to the third, which is going to give you, not negative 3, it's 10 to the third, which is going to give you 10 to the minus 9, which is a reasonable value for a capacitor. So at this point, it's like, okay, well, let's just pick a value for R1. Now, this is where, if you were actually designing this, what I would say, quote, in a real life situation, we'd want to pick components that are readily available, and so you might want to play with the numbers. For instance, if you pick 1, you're going to get 11.37 nanofarads, which we don't really have an 11.37 nanofarad. But for instance, we could try something like, for instance, maybe trying R1. I'm just going to take a guess here of, let's let R1 be 2.2K. Okay, now we could let it be 1K. There's no reason we couldn't do that. But then C is going to be 11.3 microsecond per rad divided by 2.2 kilo ohms. So let's see what happens when we get that. So we get 5.17 nanofarads, which again is not a standard component. I mean, we have 4.7 nanofarad. I mean, you can get 5 nanofarad capacitors, but again, what is mass produced? And this is not a mass produced capacitor. So maybe I'd go back and, for instance, this is where, if we're talking about real components, there's a little bit of guess and checking, because then maybe what I do is go back and say, okay, well, instead of using a 2.2 kilo ohm resistor, let's use 4.7 kilo ohm resistor, and then you would wind up with a 2.4 nanofarad capacitor, and we have 2.2 nanofarad capacitors. So you can kind of see, you can kind of keep playing this game back and forth to get to something. Now, as far as on exams in this course here, we are okay with just picking, theoretical values. Even I'm not going to be concerned about the realistic values. That's more for the lab courses where we are going to be concerned about that, because we are going to be doing this. But for now, we're just going to be okay with any kind of theoretical value. Alright, so this gets me R1 and C. And remember, this gets me my cutoff frequency to be equal to 14 kilohertz. That's what these two things get me. Now, the last thing I need to get here is we need to find R2, so gain is, well, if we look at what it was specified was in decibels. Okay, so we need to convert this back to my normal gain, because remember my gain formula here is minus R2 over R1. Now we could go ahead and convert this, logarithmic wise, what this would be, but we're going to have to convert it back either way. So I'm going to do 30 decibels divided by 20 is equal to the logarithm of the absolute value of AV. And so then you'd have 10 to 30 over 20 is equal to the magnitude of AV, which if you think about it, if I do the magnitude of AV, that would just be R2 over R1, because the magnitude of AV would be the magnitude of minus R2 over R1, which would just be R2 over R1. Alright, so we need to again do a computation here. So we have 10 to the 1.5, because 30 divided by 20 is 1.5. Just double checking my computations here for a second. Yep, that is correct. So I get 31.6. So I get that this is equal to 31.6. So that's the gain I need to get out of this. And so then, well, if I look at that, well, it's pretty easy at this point because I have R2 over, I know what R1 is, which is 2.2 kiloohms, has to be equal to 31.6. So R2 is just 31.6 times 2.2 kiloohms, which, doing that computation, we get, essentially rounding it, I'm just going to round it, we get this as 70 kiloohms. So if we go back to the original circuit that I had here, what do we have here? Well, we have that R2 is 70 kiloohms, R1 is 2.2 kiloohms, and C, what was C? 5.17 nanofarads. So now our design is done. We have an active filter here that has a gain of 30 decibels and a cutoff frequency of 14 kilohertz. Now, as a side note here, let's just remind ourselves what we had discussed in the previous video. This corner frequency of 14 kilohertz gives me that the magnitude of the voltage gain at 14 kilohertz in decibels is going to be 27 decibels. And again, why is that? My max dB is 30, so minus 3 dB is, of course, 27.